Alcohols, of course, form a homologous series. So if I just have a little table here where we emphasize that fact and have some physical properties. So all I've done here is I've taken the first 6 straight chain alcohols, so methanol, ethanol, propan 1-ol, butan 1-ol, pentan 1-ol, and hexan 1-ol. Thrown in there as well, propan 2-ol or isopropanol, which of course is something that you probably used to have on your shelves until everybody started getting it for COVID. So anyway, formulas of those, just to emphasize the homologous nature of them. So we got a methyl, then the OH ethyl, then the OH propyl, isopropyl, butyl, pentyl, and hexyl, then the OH. Boiling points of these, as you would expect, increase as the mass of the alcohol increases. That's a very standard phenomenon. Similar molecules, the heavier they are, the higher their boiling points, the higher the melting points. Didn't put the melting points here because there's actually a little twist that I didn't want to get into, in which ethanol and propanol kind of dip before you get back into that nice little series, but we don't care about that. Boiling points going up as we expect. Now it is important to note, of course, that if you're just considering dispersion forces, boiling point depends effectively primarily on the mass, molecular mass of the substance. But if I go ahead and I compare the alcohols to similarly molar massed alkanes, then I see there's a very significant difference here. Okay, so the mass of methanol is 30, mass of ethane is 30. Okay, the mass of ethanol is 46, the mass of propane is 44, and so on and so on and so on. So you'd expect them to have very similar boiling points. They don't. Look at how much higher methanol is than ethane, ethanol is than propane, propanol is than butane, and so on and so on and so on. And of course, you know, I hope, because you are all aware of intermolecular forces, that is because alcohols can hydrogen bond. As they hydrogen bond, they hold together more tightly in the solid state and in the liquid state, which means that it's harder to melt, and in this case harder to boil the particular substance that has the hydrogen bonding. Now I'm going to throw in the listed density just to show that it's not really a trend here, sort of seeping upwards as the molecules get heavier, but nothing significant. So in other words, density doesn't have anything to do with it. It is very much a hydrogen bonding thing. Now I do want to note though that the effect of that hydrogen bonding decreases as we go down the series. Look at the difference that the hydrogen bonds make with methanol. Okay, I mean that's about 150 degree difference. Then you get down to ethanol, about 140 degree difference. Propanol, only about 100. Butanol, only about 80. Pentanol, about 60 or 70. And then you get down here to hexanol, about 60 degree difference. So the effect of the hydrogen bonding decreases as you go down. And the reason for that is because as you go down this list, you not only have the OH group, but you have increasingly bigger organic chunks here. These organic chunks are, of course, hydrophobic. They don't like water, or more effectively, water doesn't like them, right? You've got this large, getting larger organic group getting only involved in dispersion. And of course, water, looking to make hydrogen bonds, hates anything that only can do with dispersion. So we see this not only in the decreasing effect of the hydrogen bonding on the boiling points, but we also see it with the solubilities, where in water you can dissolve however much methanol, ethanol, or either the propanols in water that you want. That's what miscible means, completely mixable. Butanol, however, you can only make a 10% solution, pentanol only a 3% solution, hexanol less than a 1% solution. And that's because as you get to butanol, pentanol, and hexanol, again, you've got this nasty carbon mess here that is diminishing the amount of the molecule that water wants to interact with. Of course, you also see this as we look at the solubility in hexane. Methanol hardly soluble in hexane at all, but as you start providing the hexane with more and more and more carbon atoms with which it can form dispersion forces, then you get miscibility all the way down. So essentially, as we go down the group, the effect of hydrogen bonding possibility decreases, and the importance of dispersion forces as the dominant form increases.